Lecture 7, Module 2, DMAIC, Analyze Stage 2. Verify cause and effect, tests for relationships. In this module, we'll be looking at tests for relationships, so looking at scatter plots, matrix plots, correlation, and regression analysis. First, our question is, are there any relationships? And we answer that question by looking for correlation using scatter plots, matrix plots, and we also look further with using regression analysis with fitted line plots and the analysis of residuals. Now, how strong are the relationships? Remember, all processes have inputs and all processes have outputs. Often, but not always, the outputs are strongly related to these inputs. Correlation analysis. Depending on the number of inputs to the process, use either a scatter plot or a matrix plot to examine them. If you have one continuous input and a continuous output from it, check on the scatter plot in Minitab. If you have multiple continuous inputs and continuous output, look at the matrix plot. Below is a scatter plot showing a very high positive relationship. As the x goes up to the right, then the y goes up as well. And below is a scatter plot showing a high negative relationship. So as x goes up to the right, y comes down from the left. And below is a scatter plot showing no relationship, although Minitab can draw a line through this mess. Below we see three scatter plots indicating varying degrees of relationship. All the way to the left we see a scatter plot that has a high degree of positive relationship between our x and y data. The data are clustered tightly on that line. In the middle we see a scatter plot with a moderate degree of positive relationship between the x and y data. The data are more loosely associated with the line. And finally we see a scatter plot with a minimal or probably no degree of a positive relationship between the x and y data. The data are scattered very widely around the line, very randomly. Now Minitab will draw a line through any sets of data you present to it, and it's up to us to decide whether that line is legitimate to accept or not, and we'll see how to do that when we get to residuals analysis. Now here's a matrix plot. These plots can show relationships between several related variables or non-related variables. The matrix plot below shows relationships between height, weight, brain size, and IQ. We see a high degree of positive relationship between our height and our weight. Naturally, the bigger, the taller we get, the more we're going to weigh. We also see a fair degree of positive relationship between our height and weight with brain size. The bigger we are, probably the brain is going to be larger also. However, we see no relationship between our height, weight, and the brain size with IQ. So it's not a matter of how big you are, how smart you are. You can be small and smart or large and smart. Size has nothing to do with it. Once we determine that there is a relationship, we want to know how strong the relationship may be. Now, depending on the number of inputs to the process, the regression analysis is performed differently. If you have one continuous input and continuous output, we do a simple regression using the fitted line plot in Minitab. If you have multiple continuous inputs and continuous output, we do multiple regression using the regression feature in Minitab. Indicators of correlation. The coefficient of correlation, R or large R, is a measure of the strength of the linear association between two variables. Correlation coefficients range from 0 to 1.0 for positive relationships and from 0 to -1 for negative relationships. Then there's the coefficient of determination, R square or large R square, or just written out as R square. This is a measure how well the least squares equation from your linear model performs as a predictor of the y's. The coefficient of determination ranges from 0% to 100%. So this value tells you how well your model predicts the outputs. Now note, correlation does not necessarily imply causation. There may be other factors at play, so be very careful of not confusing those two. Now here we see a fitted line plot showing excellent linearity. The R square is 100.0%. There we see the R-square 100%. Actually, this data was developed in my kitchen. You don't have to have a Nobel laureate laboratory to do good science. Now the correlation coefficient, the table below shows suggested ranges for interpreting R values. Now if the value is from 0 to 0.09 or 0 to negative 0.09, there really is none, no correlation whatsoever. 0.1 to 0.3 or minus 0.1 to minus 0.3 is a small, probably negligible, again, probably nothing. 0.3 to 0.5 or minus 0.3 to minus 0.5, there seems to be some degree of correlation, medium. And then 0.5 to 1.0 or minus 0.5 to 1.0, there's a much stronger correlation. Values of 0.9 and above are considered very strong correlations. Now here's a fitted line plot showing a plot of data on a regression line. Minitab calculates the R-square values, which are both very good here, 99.5%. Minitab also draws the confidence interval, here 99%, for the process average and the prediction interval. The prediction interval is where you can expect the process output to be based on the model. So let's say we had an x value of 5. The y could be anywhere from this point on the line up to this point on the line. So we could expect our y value could be somewhere between those 2 points. Residual analysis. The line is created using the least squares method in this regression model. The least squares method finds the best line by minimizing the total squared error between the actual value of the data and its calculated point on the line. The difference between the calculated point and the actual data point is called the residual. These residuals are important. Analysis of them can reveal if the model is a good fit and how good, or if there are any problems that we may want to know about. So let's look at that. Here's a Minitab residual analysis, and you can have, when you do the regression analysis, you can ask for these plots to be plotted for you. Now the residuals should have a normal distribution. And in the normal probability plot, we see most of the residuals fall on the line, but one residual in particular seems out of place. In the histogram, we see the residuals do not appear normal, especially not one special residual point. In the residuals versus fits plot, we again see the outlier and an apparent additional outlier while most residuals lie near the fit. And in the residuals versus order, now this is the order that the data is collected in, or the observations are obtained. We see the residuals are scattered randomly about the line, except in 2 places where they seem extreme. Now, this may be a flag that something was wrong with the analysis at that point, and it may be a call to go back and reanalyze those samples, or retest them or repull them, because something is quite wrong with these data points, and the model may be a better fit now. Here's a regression analysis where the residuals tells another picture. Although the R-square value may look acceptable enough to consider a relationship linear, this residual plot suggests that the linear model is not a good fit. It is very possible that a quadratic model would be a better fit. Now summarizing, are there relationships and how strong are they? First, graph your data and look for a possible relationship. Use scatter plots and matrix plots depending on what kind of data you're working with. Second, check for possible correlations. The Pearson correlation coefficient, R, will tell you something, but don't go solely on that. Third, perform your first regression analysis. Use the fitted line plot, simple linear regression, or multiple regression using the regression as shown earlier. Fourth, evaluate the regression. You look at your R-square, and then, of course, the residuals analysis to make sure that there's nothing wrong with the data that you are working with. And then finally, fifth, perform a second regression if the analysis indicates that it's necessary, looking to see if maybe a quadratic or a cubic model may be a better fit. This is usually rare.